One of the most striking elements in the Earth's crust is gold. Its rarity, luster, and resistance to corrosion make it an ideal symbol of value, and one that has underpinned the world's currencies throughout history. But there are other uses for gold, such as in dentistry or microcircuitry, which indicate that a fuller understanding of the properties of elements is needed to appreciate their true worth to technology. One of the most important clues to these properties comes from the periodic table. In this program, we're going to look at the periodic table and see how the order it imposes on the elements gives us a way of interpreting their properties. We can think of the elements around us rather like a group of chess pieces. Observed without context, their individual properties seem rather random, interesting, but hard to deduce much. If we can impose the right framework, we can see an underlying structure that gives the relative properties of each piece some meaning. If you're a chess player, you can see it's checkmate. White is mated. The sheer variety of elements is, of course, greater than that of the chess pieces, and we're going to start off by exploring how some of them behave, beginning with the most common element of all, oxygen.
The bubbles on the leaves of this plant are oxygen. It's a colourless, transparent gas. It's because air contains some oxygen that our fires burn. If this splint is tapped out, the oxygen in the jar rekindles it. To stay alive, we have to breathe oxygen gas. But this element, chlorine, is a gas that we mustn't breathe. It was the first of the war gases. In the First World War, thousands of men were killed or maimed in chlorine gas attacks. There are two more chemical elements in these balloons. The red one contains hydrogen, the yellow one, helium. They're both colourless transparent gases, and both are lighter than air. Because of this property, both elements were once put to a particular use, and they still are at fairgrounds. But in their chemical behaviour, hydrogen and helium couldn't be more different. Hydrogen burns with a fiercely hot flame.
It bursts into flame. Wait, get it started. It's bright, and it's bright. It's bright and terrible. Oh my, get out of the way, please. It's burning, bursting into flames, and it's falling on the mooring mast, and all the folks between us. This is terrible. This is the worst of the worst. Oh, it's 20, 400 or 500 feet into the sky.
Disasters like this would never have happened if helium had been used instead of hydrogen. Helium doesn't burn. Indeed, it doesn't react with anything. So today's manned balloons are lifted by helium. But most of the chemical elements are not gases, but solids. A few solid elements are non-metals like sulfur, which sometimes occurs beside volcanic springs. These two probes are wired to an electric bell. I can use them to find out if things conduct electricity. Now here's a very handsome looking lump of sulfur. I'll touch the probes across it. Well, that doesn't ring any bells. Sulfur is a non-metal, and non-metals hardly ever conduct electricity. Now here's a lump of aluminium. Aluminium is a metal, and metals are good conductors. Now most of the solid elements are metals like aluminium, yet even among the metals there's great variety of behaviour. Mercury is a liquid at room temperature. Cesium melts in the hand. To melt iron, you need a furnace as hot as this. And much higher temperatures are needed to melt this element, tungsten, the metal with the highest melting temperature of all. Yet amid all this bewildering variety, there is a pattern, although it's quite hard to find. Scientists call this pattern the periodic law. Whenever it's mentioned, the name of one man springs instantly to mind, a man born in 1834 amid the forests of Siberia, Dmitry Ivanovich Mendeleev. At the March meeting of the Russian Chemical Society, 1869, I communicated a paper on the correlation of the properties and atomic weights of the elements. The substance of this paper is embraced in the following conclusions. 1. The elements, if arranged according to their atomic weights, exhibit an evident periodicity of properties. Today, we use atomic number where Mendeleev used atomic weight. But what did Mendeleev mean by periodicity of properties? Let's try to find out by laying out the elements as he laid them out in this book. We'll ignore hydrogen and start with element number 2, helium. The 8th element in this row is fluorine. Next comes neon. Now neon resembles helium in two very obvious ways. First, it's a gas, and second, it doesn't react with anything. We'll mark this similarity by putting neon underneath helium. Off we go again. Another row of 8, and we get a sign that we're on the track of something very fundamental. The next element is argon, and again, it's a gas which doesn't react with anything. So argon goes beneath neon, and off we go again. Let's stop there at scandium. The vertical columns of this arrangement are called groups, and the horizontal rows are called periods. What we have here are the beginnings of a periodic table. The groups are numbered from 0 up to 7. The most important thing to remember about the periodic table is that the groups contain elements which resemble each other. Let's look at the elements of group 0, the noble gases. When it's complete, it contains 6 elements: helium, neon, argon, krypton, xenon, and radon. Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colorless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
So the elements in a group have similarities, but of course they also exhibit important differences. These variations usually have some regularities, and these regularities are related to the progress through a group. To illustrate this, let's look at the elements of group 1, the alkali metals.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
And that seems a convenient point to break off our study of the alkali metals. The groups contain similar elements. That's the most important thing to know about the periodic table. The next most important thing is that trends or regular changes occur as we move across a period. To demonstrate this, we'll use this period, the one that runs from neon to chlorine.
We'll look for a regular change by reacting these elements with this element, fluorine. Fluorine is the Tyrannosaurus rex of the chemical elements. It reacts, often ferociously, with nearly all the others. Now neon, the first element in the period, is a noble gas. Even fluorine won't react with that. That's a pretty flat beginning, but don't worry, things will soon warm up. The next element is sodium. Fluorine gas is delivered through the tube on the left. See how violent the reaction is. We'll react magnesium in the same way. Now for aluminium. This time, we'll tip aluminium powder into a jar of fluorine gas. We'll try silicon in the same way. With phosphorus, we'll go back to using a stream of fluorine. And with sulfur, we'll show you both methods. A flash and a burn.
It's hard to believe that among that series of fireworks there was a regular change, but there was. If you just stand and peer at the reactions, you miss it. But you see it if you look at the formulae of the compounds that are formed. Let's look at the number of atoms of fluorine that one atom of each element combines with.
Neon, 0. Sodium, 1. Magnesium, 2. Aluminium, 3. Silicon, 4. Phosphorus, 5. In each case, the products of the reaction are the highest fluorides of the elements. The number of fluorines increases in steps of 1 from neon to phosphorus. So, what formula would you predict for the highest fluoride of sulfur? If you said SF6, that's right. Fluorine reacts with sulfur to form sulfur hexafluoride. Now, what would you predict for chlorine? I expect you said ClF7. Well, there you were unlucky. The highest fluoride is in fact ClF5.
This failure is just one instance of a very important limitation of the periodic law. Very often, periodic trends are neither as precise nor as regular as we would like them to be. But those trends are there all right.
Well, at this point, I don't want to develop the structure of the periodic table much further. You'll find that in the unit. But one thing the complete table shows up very clearly is the difference between metals, semi-metals, and non-metals. Metals on the left, of course, the largest grouping, and non-metals on the right. But can we say anything about the uses of different elements from the periodic table? Well, we can take the clear distinction between non-metals, semi-metals, and metals a bit further. Many non-metals are gases, like the oxygen and nitrogen here in the air. And we've seen some of the uses of light gases in balloons. Because of their low liquefaction point, helium and hydrogen are also both used in liquefied form for the production of low temperatures. For example, for superconducting magnets or refrigeration purposes. We've also seen some of the more reactive gases like oxygen and fluorine. We shouldn't forget that their reactions can also be a nuisance, as in corrosion. By the same token, inert gases like argon can have uses in industry for just the opposite reason. In this factory, for example, argon is being used to create an inert atmosphere for the production of special plastics. Argon is selected as one of the cheaper inert gases. In a normal atmosphere, some oxidation can be expected to occur, and this can induce critical degradation of the material. This would be important, for example, if a plastic is to be used for optical transmission purposes, as is this one. But of course, not all non-metals are gases. Carbon is another non-metal with special uses, the most dramatic coming from the diamond structure of the element. Diamonds can occur naturally, and the purest specimens are usually selected for jewelry and ornamental purposes. But the hardness of diamond also makes it valuable in industry for the cutting of very hard materials. In contrast, another form of carbon is very soft. That's graphite, and it's used in lead pencils, for example. But carbon also conducts electricity. If you've ever pulled apart a dry cell, you'll know carbon is used as one of the electrodes. Now, graphite also forms the electrode in a number of commercial electrolytic cells. Now, electrical properties are of some special importance, and another group of elements are the semiconductors. They're used, for example, to produce the transistors in this radio. Early transistors were made from germanium. But the microelectronics revolution has led to a change in the element used. The most common semiconductor is silicon, and its most important use is as the base element for the production of microchips. In fact, a large number of circuits can be created on the same chip by the careful arrangement of many tiny circuits. This process is being refined almost every year as new manufacturing techniques are evolved. But of course, the connections to microcircuits use metals. In fact, metals form the largest grouping of elements used in our everyday lives. There are many ways of classifying metals, but an interesting way that has some predictive value is through the way the metal is retrieved from its ore. David Johnson explains.
I want now to float an idea at you. We've looked at gold, which occurs in nature as the metallic element. We say that it occurs native. Then there's iron, which is made by heating ores like ironstone with carbon. Finally, there are metals like aluminium, whose ore is bauxite. Bauxite can't be converted to the metal by heating with carbon, even at blast furnace temperatures. Suppose we classify other metals in this way. Does such a classification have any value? Here are some common metals classified in this way. In the first set with gold, I've put silver, mercury and copper. Gold and silver are used in jewellery and ornaments. You'll be familiar with mercury from thermometers, and copper is used for electrical wiring. Significant proportions of all these metals occur native, or, as in the case of mercury, can be made simply by heating this sulfide ore in air. In the second set, with iron, I've put tin, lead, and zinc. Iron and tin occur as oxide ores, lead and zinc as sulfides, but the sulfides are easily converted to the oxides by heating in air. The four metals are then made by heating the oxides with carbon. 3 of the 4 metals occur in the Land Rover. The engine block is made of iron, there are lead plates in the battery, and the bumper is plated with zinc. As far as I know, there's no tin in the vehicle, but my lunch is in this can, which is tin plated. In the third set of metals, with aluminium, I've put magnesium and sodium. Aluminium is made from bauxite. A lot of sodium and magnesium is made from the dissolved salts in seawater or underground brines. You'll be familiar with aluminium, and magnesium is used in flash bulbs. We haven't brought any sodium with us, and perhaps you can remember why. We were afraid that it might rain.
Well, metals like zinc and the chromium plated onto this bell are well known for being non-corrosive. For this reason, they're often plated onto metals which are likely to corrode. Of course, some other metals don't corrode easily. For example, metals like gold or platinum or tungsten. Now, another key factor in the use of elements is, of course, their cost. This is measured nowadays for many elements by their price on the open market, where many metals in particular change hands every day in frenetic activity. Metals commonly exchanged here include zinc, aluminium and copper, as well as the precious metals. The final point I want to make is on the relative abundance of different elements. What stands out is how 1 or 2 elements dominate our Earth's crust. Oxygen, for example, accounts for more than 1/2 of the Earth's crust. What's surprising is just how rare some of the elements we take for granted in our everyday lives really are. The graph would be changed somewhat if we penetrated beneath the Earth's crust into the core, although the inclusion of the Earth's atmosphere would add yet more oxygen to the tally. If we go beyond the Earth, well, that's beyond the scope of this program and beyond the foreseeable benefits for modern technology.